In the previous class, we have seen the regularity of Borel measure. Today, let's observe a kind of condition which can ensure the regularity of a measure or a Borel measure. Let it be formally stated as a theorem. So the theorem states that let X be a locally compact host of space, a locally compact and host of space in which every open set is sigma compact. In which every open set is sigma compact. I hope you remember the definition of sigma compactness. So every open set is sigma compact. Let lambda be any positive Borel measure. Let lambda be any positive Borel measure. So lambda is a Borel measure, means it's defined on a sigma algebra which contains all its Borel sets. Right. So lambda be any positive Borel measure such that lambda of k is finite for every compact set k. For every compact set k in X. So the measure of every compact set in X is finite with respect to the measure lambda. If it is the case, then lambda is regular. Right. So this is what we need to prove. So this actually works as a sufficient condition to ensure the regularity of a Borel measure. Right. Go through the statement once again. Let X be a locally compact host of space in which every open set is a sigma compact set, which means every open set can be expressed as a union of countable or a countable union of compact sets. And let lambda be any positive Borel measure such that lambda of k is finite for every compact k in X. Then lambda is regular. So before moving to the proof, can we think about an example of a space with these properties, a locally compact host of space with every open set is sigma compact? See, this may seem a little complicated, but our examples of the normal Euclidean space Rk or Rns are examples, perfect examples for this case, where every open set is a sigma compact set. See, in Rn, any open set or any open set can be expressed as a countable union of closed balls, and closed balls are obviously compact. Right. For that reason, Rn is a space in which every open set is sigma compact. Right. So this makes the theorem a little more significant in its practical applications. So now let's move to the proof. Let's consider a functional lambda of f defined to be integral over x f d lambda. Yeah, we have seen this in the statement of raised representation theorem, and obviously we use the same concept here. So lambda of f is defined as integral over x f d lambda. Obviously lambda of f is defined on CCX, the set of all functions on x with a compact support. Right. So since lambda of k is finite for every compact set, this lambda will be a positive linear functional, since f comes from the set of all functions with a compact support, and the measure of compact sets are finite, and for that reason this is actually a positive linear functional on CCX. Right. Now we have seen that from Rees representation theorem, if we have a positive linear functional on CCX, then we can immediately find a measure mu such that lambda of f is equal to integral over x sum f d mu. Right. We can identify, or we can find a measure mu which can represent the linear functional lambda. We defined lambda to be integral over x f d lambda. Then we move towards a little more convenient form as lambda of x, integral over x f d lambda equal to integral over x f d mu. Right. This mu comes from the Rees representation theorem, and remember, this mu is not just any measure, it has certain properties. That the previous theorem, very previous theorem stated that this mu coming from the Rees representation theorem is in fact regular. Right. Now we have the statement integral over x f d lambda equal to integral over x f d mu, and if we can show that lambda equal to mu, then it's easy to claim that lambda is regular since mu is regular. Right, so that will be our strategy for this proof. We will show that lambda equal to mu, and since mu is regular by previous theorem, we claim that lambda is regular. Right. Okay. So let V be any open set in X. Let V subset of X be an open set. Then, since we have an assumption on X that every open set is sigma compact, V can be expressed as a countable union of compact sets. Right. Moreover, the measure of each compact set is finite. Now, by Eurison's lemma, we can choose FIs. Eurison's lemma assures the existence of such FIs with the property Ki related to Fi in such a way that I hope you remember this symbol. What does it mean? Right, we have seen that in the last class. So we can find FIs such that this arrangement holds true. Now let Gn is equal to maximum of F1, F2, etc. Fn. See, for each choice of Ki from this union, we will be having different FIs maybe. We don't know. So we choose Gn to be the maximum of them all. And see, this Gn, each of these FIs are actually somewhat, we try to identify this as the characteristic function of V in certain manner. And for that reason, Gn of x as a function increases to the characteristic function chi V of x at every point of x. At every point of x belongs to x. Right. So this will gradually increase to or kind of convergence to the characteristic function of V. We have seen that in the previous class. So right, that's it. Then the monotone convergence theorem. We'll make use of the monotone convergence theorem, which we have already seen. Lambda of V is equal to limit n goes to infinity integral over x Gn d lambda. This holds true since limit n tends to infinity Gn is actually identified as chi V. Right. So this is how we can easily find the measure of a set. Right. So we use this definition or this idea to conclude that limit n tends to infinity integral over x Gn d lambda coincides with lambda V or the measure of V with respect to the measure lambda. Right. Then we have also seen that see this is equal to limit n tends to infinity integral over x Gn d mu. This is possible since we have seen that integral over x f d lambda is equal to integral over x f d mu using that positive linear functional lambda f. Right, we have seen this a little ago. So using that identity we claim these two to be the same, right? So now this is nothing but if limit n tends to infinity gn is chi v, this is nothing but the measure of the set v with respect to the measure mu, right? So lambda of v is equal to mu of v for any open set v. But this measure lambda comes from a sigma algebra in which all the Borel sets are contained. So simply claiming for an open set won't suffice. So now let's see what happens for a Borel set. Let E be any Borel set in X. Choose epsilon positive to be arbitrary. See that mu we found was actually holding several properties like regularity and the previous theorem in which we found that there exists closed set F and an open set V such that F is contained in E contained in V and measure of V minus F is less than epsilon. This is true since this mu comes from the Rees representation theorem, and by the previous theorem we have seen that this mu satisfies this property, right? Then measure of V with respect to mu is less than or is equal to measure of F plus say epsilon, right? Yeah, from the additivity properties, and since F is contained in E, this is again less than or equal to measure of E plus epsilon, right? So measure of V is less than or equal to measure of E plus epsilon. Since V minus F is open. See, V was an open set and F is a closed set, and since V minus F is open, measure of V minus F. Oh, wait. V minus F is open, and we have seen that for open sets, measure of lambda of V or the measure with respect to lambda is equal to the measure with respect to mu. We just seen that a little ago, and for that reason, since V minus F is open, mu of V minus F is less than epsilon implies lambda of V minus F is less than epsilon. So since we have seen mu and lambda coincides for any open set, mu of V minus F is less than epsilon implies lambda of V minus F less than epsilon. This means the measure with respect to mu and the measure with respect to the measure lambda, right? And the measure lambda of V minus F is less than epsilon means the same argument again, means lambda of V less than or equal to lambda of V is less than or equal to lambda of E plus epsilon from this expression and the subadditivity property of or the additivity property of measure, right? We had a similar expression with mu of V is less than or equal to mu of E plus epsilon, right? So yeah, consequently lambda of E less than or equal to lambda of V, which is equal to, from this expression, which is equal to mu of V, which is less than or equal to mu of E plus epsilon. Also, mu of E is less than or equal to mu of V, which is equal to lambda of V, since V is an open set and mu and lambda coincides for open sets, which is less than or equal to lambda of E plus epsilon. Right. Then, from these two expressions, combining these two, we'll get mod absolute value of lambda of E minus mu of E is less than epsilon, and this epsilon was arbitrary, which can be any positive number, and the lambda of E minus mu of E has an absolute value less than epsilon, means it actually goes to 0, or lambda of E is equal to mu of E, and this is true for any Borel set E, and for that reason we can claim that lambda and mu are the same, and since mu is coming from that Rees representation theorem, which is proven to be regular, lambda is regular. So this is what actually we wanted to prove. So what do we do now? We consider the positive functional lambda of f, which was defined to be integral over x f d lambda, and with the same positive functional lambda, using Rees representation theorem, we found a new measure mu such that lambda f is equal to integral over x f d mu, and the strategy is to show that lambda equal to mu. Since mu is proven to be regular, lambda will be regular then, and we have shown that lambda and mu coincide for open sets first, and then now we have seen that lambda and mu actually coincide for not just open sets but also for any Borel set. So as Borel measures, lambda and mu are the same. That's about the condition which ensures that a measure is regular, a Borel measure is regular. And now we are going to discuss about Lebesgue measures. Before moving to Lebesgue measures, we have to revisit some basic and fundamental ideas. So I hope you perfectly remember the definitions and properties of Euclidean space. So what do we mean by the Euclidean space Rk? It's quite that simple. It's the collection of all those points of the form x1, x2, etc. up to k entries xk, where each xk are real numbers. So there is no point in repeating these things in a PG classroom, but still, as part of completeness, for the sake of completeness, we got to tell all this. So Rk is the collection of all k tuples, where each entry is a real number, right? And you know how to operate between two k tuples, how to add them, how to subtract them, and how do we perform multiplication with a scalar or a non-k tuple or a single entity of real number, right? And all those operations makes or gives this Rk a structure of a vector space, and we have certain other operations as well. I hope you remember certain equalities and inequalities with the absolute value. I hope you remember the absolute value of a k tuple, let A to be a k tuple, and the absolute value of A is defined as that Euclidean distance thing, right, from the origin. And you remember the Schwarz inequality, Schwarz inequality. If xy from Rk, then mod xy will be less than or equal to mod x mod y. Okay, and this in turn leads to the triangle inequality. Mod x minus y is less than or equal to mod x minus z plus mod z minus y. So these are just fundamentals. In fact, this modulus operator or this absolute value thing or the distance concept actually gives rise to the metric or the distance function rho of x y equal to absolute value of x minus y. Right, this actually gives the distance between x and y. That's what we call a metric. And using this, Rk gets the structure of a metric space as well. Okay, so Rk has a structure of topological space, we'll find that, and Rk has the structure of a metric space, and Rk has the structure of a vector space. Alright. So now we may define a few more basic concepts like you know what is the translation of a set E plus x. E plus x is a new set. If E is a subset of Rk, then E plus x is defined to be the set, say y plus x, where y is in E. So X is added to every element of V, and that's how we translate a set in Rk. Right. All of these things and these words or these concepts have some geometrical implications too. And those who are interested can think about that. So another thing is let X to be, say, X to be given as some X1, X2, etc. into Xk maybe. So the set W, which is defined as the set of all X such that some alpha I less than xi less than some beta I for I, so 1 less than or equal to I less than or equal to k. Since we are talking about Rk, k is the limit here. Right. So see, each of these X consists of k coordinates or k components, x1, x2, etc. Up to xk, and we are trying to put limits for them. And such a set with these limits holding true are called a K cell. A K cell. So a K cell is a set of the form W is equal to set of all elements from Rk X such that alpha I less than. See, whether this is less than or equal to does not make any change. We call it K cell itself. Right. So alpha I less than or equal to xi less than or equal to beta I for I running between 1 to k is called a K cell. And the set for if A belongs to Rk and delta positive, the set Q of A delta, which is defined as set of all X such that, say, alpha I less than or equal to xi less than alpha I plus delta, 1 less than or equal to I less than or equal to k, is called a delta box with corner at A. Delta box with corner at A. See, these are not that important concept for now, but you have to get convinced with these things. These are better explained in the textbook, and you can refer that in detail. These two are the major concepts which we may use in the following and the further analysis of Lebesgue measure, and we have two more concepts to introduce. Let n be any natural number, and let Pn be the set of all X belongs to Rk, be the set of all X in Rk, such that the coordinates of xk are integral multiples of 2 raised to minus n. So Pn is the collection of all X in Rk's such that coordinates of X are integral multiples of 2 raised to minus n. This is how we define Pn, and a new set omega n is defined as omega n to be the collection of all 2 raised to minus n boxes. See, how did we define a delta box? The same way you can think about 2 raised to minus n as delta, since 2 raised to minus n is always positive. So 2 raised to minus n can be considered as delta with corners at the points of P. With corners at the points of Pn. So delta omega n is the collection of all 2 raised to minus n boxes with corners at the points of Pn. So simply remember this concept. We may not be using this extensively, but we may use certain concepts of these in the following analysis. And from the next session onwards, we can start our analysis on Lebesgue measure.